I want us to start with, so we have an entire day of moderation workshop where you have a whole, like 14 moderation examples, and you work through a few of them with your group, and then you have all of the rest to take with you to practice at different points. Today's objective, explain moderation, talk about how centering reduces multicollinearity. So remember when I told you we always center predictors, and I was like, it makes the intercept interpretable. And later down the line, it will help with multicollinearity. That's today. Figure out whether moderation is significant or not using the correct way, interpret moderation graphs, generate moderation equations, define the concept of simple slope. That is a really key concept coming out of today. Correctly interpret simple slope hypotheses and communicate those findings, and then use those equations to be able to predict values or graph, etc., and be able to communicate those results. Both, obviously, APA when you're doing your write-up. I actually think the harder one is the storytelling component. Cool. I want to take us from where we started to where we are now, even if you don't draw it. If you are interested in hypothesizing that, which you might be, then you might label it. So you might say, this is my first hypothesis, this is my second hypothesis, and then my moderation is my third hypothesis. Or you might not. Let's think for a second. Why do you have to, when we compare models, we're always going to compare a model with just the main effects? I think what you're asking is, it's here. It's not that there's another line, it's that these models, parental support to job performance, moderated by newborn awake time, that these two theoretical models are different conceptually. Theoretically, they are identical statistically. The stories are different. If I'm telling this big story, I'm saying, hey, newborn awake time, the more your kid's awake, the shittier your job performance. It turns out it doesn't impact it as much if you have high parental support. That's this story, story one. This story is, hey, if you have a lot of support from fellow parents, that makes your job better. But that parental support matters less if you have a kid at home who stays up all the time. That's story two. That was harder to tell because it doesn't make sense. Statistically, identical models. Why? Because the way that we form that interaction is we just multiply our two predictors, which we're going to get to in about 3 slides, and your theoretical model. Yep. And how you report it. So you're going to have your theory. That's why we model build. That's why we don't just run stats. We're like, here's our theoretical model and our hypothesis. I'm not going to say I hypothesize newborn awake time moderates. I'm going to say I hypothesize parental support moderates the relationship between newborn awake time and job performance such that this relationship gets less strong when parental support is high. And then statistically, this is how I'm going to test it. When I interpret my results, again, I'm going to interpret it in the context of my what? Always. What's my North Star? No, you always want to say what you found in truth. You don't switch what you hypothesized. All right, should we do this? All right, cool. You guys are such good question askers. We're going to do an example. The literature suggests that income, the degree to which people like their job. So we're going to look at job interest as a moderator here. So what's my research question? Does the relationship between income and quality of life depend on how interested someone is on their job? If you want to be really statsy about it, does job interest moderate the relationship between income and quality of life? But really, nobody wakes up in the middle of the night and is like, does this moderate the relationship? It's more going to be like, everyone says income matters. I wonder if it depends on how much you like your job. I like the word depends when we're thinking research questions. Cool. So now I have to write my hypothesis. Couple important things to note in your hypothesis section. Job interest moderates the relationship between income and quality of life. That's part one, the moderates. What's the problem with just saying job interest moderates the relationship between income and quality of life? How? In what direction? One thing that can help you is to label. So what is the relationship between income and quality of life? Positive or negative? No. Positive. And when job interest goes up, always as your moderator goes up, that's important to understand. As your moderator goes up, is this relationship going to become stronger? This is the starting premise, no moderation. We're starting with the premise that if you make very little, your quality of life is low. And if you make a lot, your quality of life is high. Positive relationship. We're saying that that might matter less if income is high or if interest is high, which means that relationship is going to be weaker. This is one of the things that's challenging for people to wrap their head around in moderation. I've got lots of examples of it at the end of this deck. So we are actually hypothesizing, oh, we should probably hypothesize that it weakens. I think it should weaken. Look, I did it. Job interest moderates the relationship between income and quality of life such that this relationship weakens when job interest is high. The other way to always say it without directionality is the degree to which income predicts quality of life. Income, quality of life. At the bottom, once we get through this example, there are 3 types of moderation effects. There's buffering, strengthening, and antagonistic. At the end here, I've got examples, lots of them, of all 3. What you're talking about, Allie, is this type. So sometimes you might hypothesize that actually a moderator is going to reverse direction. And that makes it a little bit harder to write a hypothesis because you're not saying it's just going to make this relationship a little weaker or it's going to make this relationship a little stronger. You'll notice I did not put a direction on my H3 here. I explained it here. So I said experience moderates the relationship between exercise intensity and performance such that the relationship is negative for low experience individuals and positive for high experience individuals. I don't split my hypothesis because it's still one moderator. I'm hypothesizing different directions for different levels of my moderator, and so I'm going to include them both in my hypothesis. Does that answer that question? If we're running it in unstandardized form, you recognize this. It's just intercept B1x, B2z, and then B3x times z. In this case, it's income, interest, and income times interest. Okay? If we want to write it standardized, we just chop off the intercept. Well, now you could have other predictors in here too. That's allowed. So if you had this, you could also just have like another thing, another predictor. That's allowed. In this case, what we're saying specifically is that Z is moderating the relationship between X and Y. And we're only going to ever focus on moderating a single path. Even when our model is huge, like even when we get to path analysis, the moderator is still acting on a specific path, not the whole model. So let's get to this variance question. So we'll start with just one person. So here I am, this me, my quality of life. I've got 4 sources of variance, 4 things explaining my quality of life. My income, my interest in my job, the interaction between my income and interest in job, and then other stuff. We can also think about all the variance if I'm part of a data set. So here I am over here. I like to think I'm slightly above the mean in my quality of life. Here I am. This is the whole data set, the whole distribution of quality of life. And there are 4 things that explain all the spread. Essentially, some scores are way above the mean and some scores are way below the mean. And there are 4 things that explain where those scores fall. People's income, people's interest in their job, the interaction between those 2, and error. Cool. Identical to a what? This circle looks exactly the same as a what? Factorial ANOVA. It's the same. It's just continuous variables. That's crazy. That's because ANOVA is just a specialized form of regression. All right, so here we are. We have our general model structure. What do we have to do to actually look at moderation models? We have to prep our data in 2 very specific ways, which I will tell you about at 10:10 when we come back. The first thing you need to do is you need to center your predictors, and then you need to create a moderator term. So we always center our predictors. It's the best practice in regression. In moderation, you really need to center your predictors. Why? Because you are creating a product term out of 2 of your predictors. If you don't center them, you are creating a direct multicollinear product of 2 predictors. I'm going to show you how centering helps with multicollinearity. Remember that perfect multicollinearity means that you can predict one of your predictors from the other. So look what happens. Here's our original data, income, quality of life, and job interest. Here we have our means. So our mean of income is 85.41, and our mean of job interest is 39.85. What we're going to do is we're going to create our centered variables first. So we're going to subtract the mean of income from all of our income values, and we're left with income centered or income.c. And then we're left with job interest.c, and the means of those, remember, are what? 0, This is why when we center, the intercept becomes when X is average, because it's like plugging in the centered zero. Then we create our moderator term. How do we do it? We literally just multiply them. So first we center our predictors by subtracting the mean, and then we multiply our two centered predictors to create a centered moderator term. Good with that part? Now, why does it help with multicollinearity? Is this the most important thing from this lecture? No. So we always center in order to help with multicollinearity also. So we centered and we created a moderator term. Good. Now we're going to fit and specify and fit and compare models. The first model that people sometimes like to create is just XY. So in this case, our XY would be income to quality of life. If you specify this model first, then what do you think your second model is going to be? Income and interest to quality of life. Some people, you'll notice I say alternative model 1. It's also fine to start with this as model 1, meaning you can go straight from, I'm going to test a model with main effects and then a model with moderation. Or you can really go piecemeal. I want to just test my X, then I'm going to test what's next. Yep. So now we're going to add in the interaction. So again, you can test all three of these, or you can just test if the difference between model 2 and model 3 is significant, you have moderation. That is how we confirm that you have moderation. If your model with a moderator term explains significantly more variance in quality of life than model 2, then job interest moderates that relationship. Another way to say it without using model numbers, which is more holistic, is saying if a model with the interaction term explains significantly more variance than a main effects only model, then you have significant interaction. So yes, there is a beta for the moderation term. We don't use that to explain that the moderation is significant. We use the change in R squared. Why? Because it's the storytelling aspect. It's the idea that the interaction between these two things explains more in our outcome than just their individual main effects. Saying the beta is significant here, that's like a stats support. It's not the story. So we use the R squared as evidence. So here's our results. In this case, I ran all three. So model 1 has income, model 2 has income and interest, and model 3 has income, interest, and the moderator term. They're all significant. That's not uncommon. And here's where we want to see whether we have moderation. So is a model with both main effects better than a model with just income? Yes. Is the model with the moderation or the interaction term better than just a main effects model? Yes. Notice the R squared is small. That's normal. So moderation effects are not usually very big. You're not looking for betas of like 0.4 or 0.5. And that's because they don't represent slopes, they represent change of slopes. And I'll show you that in a second. It is not, you're not gonna see giant, so don't look at this and go, well, it's significant, not a lot. It's never going to be a lot. And I'll show you why. Are we good with this part? I feel like the model comparison part's pretty straightforward. They're called income and moderator. R does not distinguish that this moderator thing was two things that you multiplied together. That's you to know. So we're gonna interpret these different, so here's what it looks like if we were to draw out the whole equation, unstandardized. Good so far, it's the same exact thing as multiple regression. Now let's interpret them because here's where it changes. Pretty drastically, actually. All right, 6.36. This is the predicted quality of life for someone who earns average income and has average interest. Is that different? No, that's the same as multiple regression. We centered our predictors, which means we're plugging in a centered zero, a centered zero, a centered zero, and a centered zero. Functionally the average. So this is 6.36 is the predicted quality of life score when all our predictors are average. Here's where it's a little bit different. First difference. How would we normally interpret 0.46? The slope between income and quality of life, keeping everything else constant. That's how we would normally interpret 0.46. It changes in moderation slightly, and I'm going to show you why. 0.46 is the predicted relationship between income and quality of life when interest is average. Not just when you hold it constant at any value, it has to be average. Don't worry, I'm going to show you why. Only when the other variable that's acting as the moderator is average. The same is true for the other part of the moderator. This slope, 0.20, is the predicted slope between job interest and quality of life for someone with average income. So for assuming someone earns an average income, then for every 1 unstandardized increase in job interest, we'd expect a 0.2 unstandardized increase in quality of life, okay? This is new. This is a coefficient for a moderator term. Well, it's not a slope because it's got 2 variables in it. It's got income and interest. What it is a change in slope. So it's the change in slope between X and Y, or Z and Y, whichever you theorize. We theorize X and Y. So it's the change in relationship between income and quality of life for a 1 unit increase in our moderator. So now let's talk about why it has to be average and it's not just holding constant. So here we have our predicted relationship between income and quality of life when job interest is average is 0.46. So why does this slope assume job interest is average? Let's just work it out for a second. So if we plug in a 0, so remember that plugging in a 0, a centered interest of 0 is what? Average interest, right? What happens if we plug in a 0? 6.36. We reduce the equation to this. Still 0.46, yes? But what happens if we plug something other than 0 in? Anything other than 0. I just went for fun. I was like, let's do a 3. So that's 3 points above the average. Well, this part's not a problem because what happened to that? That's just a number. What happens to this? 3 times 0.02 becomes what? What's 3 times 0.02? 0.068. Now I have 0.46 ink and 0.06 ink, and I have to put them together. Now the slope is not 0.46 anymore. Now it's 0.52. Why? Because Z went up how many units above average? 3 units. And what was our change in slope? 0.02. So when it went from average to average plus 1, that 0.46 went to 0.48. When it went up another point, it went to 0.50. And when it went up another point, it went to 0.52. That's the change in slope. So unless we're plugging a 0 into the moderator, these slopes are going to change. So when we're interpreting the main effect slopes, these are only the slopes when the other variable is average. Because the interaction coefficient will change this if you put anything in here other than 0. Why does that have to be? And it relies on 2 pieces of knowledge and skill. The first is really understanding why when data are centered, plugging in a 0 means average. That's the first skill it's dependent on. The second is now why you have to plug in, you have to keep this at average. Otherwise the slope will change. What? You say that. So the 2, in order to understand what we just did, the idea of why this is the predicted relationship when the other variable is average, is relying on 2 skills. The first is just the basic concept of centering, that when you center, the average becomes a centered 0. And the second skill is the idea of why when you have a moderator term, does this slope only become this slope when this is 0 or average. Questions about this? It's just not an easy thing to wrap your head around. Good. Because our variables are centered, I'm plugging in numbers here. I'm not plugging in raw numbers. Plugging in a 3 means 3 above average. So for every, this is for every 1 point above average that interest goes up, this slope is going to go up by 0.02. Now, why am I interpreting just this one and not this one? The relationship is the same. 0.20, that's the relationship between interest and quality of life when income is average. That slope is going to change by 0.02 for every increase in 1 above in income. That's not what I theorized. So I'm keeping my income to quality of life, I'm keeping that theoretical model in mind as I interpret this. It's modeling that thing on the, so we've got main effect slopes. These are your main effect slopes, and these are slopes only when the other predictor is average. So you've got two predictors. One is serving as a regular predictor, one is your moderator. Your main effect slopes are just your slopes when the moderator or the other variable, the other predictor, is average. And then you have this new type of coefficient, which is a change in slope. And that's how much either of your main effect slopes will change for every unit increase in the other. So let's visualize this. This will help us understand what this looks like. So here's what income and quality of life look like when interest is average. So what did I plug in for Z here? You tell me. If I want to know, if I want to create an equation of a line when when interest is average, what am I going to plug in for interest? 0. Why? Let's go back here. This is super critical. Hold on. Let's go back here. Look, here's the raw data. Interest average is 39.85. When we center, what happens if this person has a score of 39.85? What's their centered score going to be? 0. And which set of variables am I putting in my actual model? These. So this person, number 100, I'm putting in their score of 0 for job interest. Are they really 0? No, they're the average. So when we're working with centered values, if I put somebody in as a 0, that someone has an average on that variable. Here's interest average. I'm going to plug in a 0. Okay? I can reduce that, and here's my equation. Y equals 6.36 plus 0.46x. Pretty simple equation. This is why moderation is a little bit easier to visualize than the three-dimensional plane, because we're going to choose average, high, and low values of our moderator, because theoretically that matches our research question. So I'm going to start with average. Well, then now let's look at when Z is 1, which means 1 point above average. So what am I going to do? Plug in 1. Now, look what happens. This is Alan to your question. This is how the intercept changes. So I've got 0.4x. This just became a what? A number. This doesn't get to be a number. 0.01x times 1, it's still an x. So I get an equation of 6.56 plus 0.48x. What if I want to look at when interest is 2 points above average? Then I can plug in a 2, and I get y equals 6.76 plus 0.5. And then we could do that 3 that we already did, which would make it 0.52x. Cool. The problem with this is what? We're moving by increments of 1 unit. If you're thinking about wanting to understand moderation, so essentially we're wanting to understand, does interest moderate the relationship between income and quality of life? So does the relationship between income and quality of life depend on job interest? Are you interested in how that relationship looks different for people who are 3 points apart from each other? No, stay with me. You're interested in how income impacts people's quality of life when they love their job versus when they hate their job. You want a high and a low, and maybe a middle. Now, you can use this to do that. What would you do? Just pick a really high value of Z and pick a really low value of Z and plug it in. Oftentimes, there's 2 problems for that. 1, you got to find a high value of Z and a low value. And 2, remember that these slopes, I know they look like you can interpret them. You can't. 0.46, 0.48, 0.50, those aren't unstandardized. Those are unstandardized. Those aren't actually like a correlation of 0.5. Those just happen to be below 0. You could end up with a slope of 2.43. How are you going to see what that looks like? So generally, when we visualize moderations, we stay away from B because it's impossible to visualize. And we use this. Here's how we generally operationalize. Oh, we already did this. Oh, this is what I did. So here's what you could do. You could manually go into your data and find what we often call high and low. Generally, the way we operationalize high and low is 1 standard deviation above the mean and 1 standard deviation below the mean. Why do we pick 1 standard deviation above and below? It's 68% of the data approximately lies within 1 standard deviation. So it's a pretty meaty, even though it's only 1 standard deviation, it's a pretty meaty high and low. Could you pick 2? Sure. whatever you want. The standard is 1. I could go look for it. I did. Turns out one standard deviation above the mean is 11.48 points, and one below is minus, and I plugged it in, and I got these equations. Cool. Still really hard to interpret because they're unstandardized. So usually what we'll do, you can see at least graphically what changes. When interest is high, the relationship, it actually does strengthen. Weird. Instead, we usually use betas. You see that? So here's the beta equation, 0.39, 0.39. Those just happen to be the same. And 0.16. That 0.02 looked really small, didn't it? Because it's unstandardized. 0.16 is actually a really decent change. Same exact interpretation. These main effect slopes are the predicted relationship between each predictor and the outcome when the other one is average. And what's this 0.16?
Change in slope.
Change in slope for a what? For a 1 standard deviation increase in your moderator, just like we interpreted it in regression. So it's not a 1 raw unit. That's why it's also a lot bigger, because what does that 1 standard deviation represent in raw units? We just saw it. It's like 11.48 raw units. It's a lot. So if we graph it, here's our average slope between income. So this is income and quality of life when job interest is average. Here it is when job interest is high. And here it is when job interest is low. It's a weird opposite relationship, actually. I wouldn't expect this. Much easier to understand because these you can interpret. That 0.23 is 0.23, like a correlation of 0.23. That 0.55 is 0.55, like a correlation of 0.55. Yep. What is it? 0.39, right? 0.39. What's the relationship between interest and quality of life accounting for income? Also 0.39. What's the moderator term? 0.16. Notice that moderator of 0.16 is pointing at the arrow. Literally, this slope is going to get bumped by this much for every 1 SD increase in interest. You could think about it like 0.39 is your existing relationship, and as interest goes up by 1, it comes in and bumps that 0.39 up by another 0.16. As interest goes down by 1 standard deviation, that 0.39 will go down by 0.16. So we could also do interest to quality of life moderated by income. Beta equals 0.16, 0.39, same relationship. It's only theoretical that we're putting the moderator in the moderator place. So here you have the relationship between income and quality of life. And it's, remember that this is when interest is what? Average. And what is that relationship? How strong is it? Good. And you can see it on the graph. Now, if we want to see the moderating effect, as in how that 0.39 is going to go up or down, we need to know what the interaction coefficient is. That interaction coefficient is positive 0.16. The coefficient for the interaction is always a change coefficient. It's not a slope, it's a change in slope. So what's going to happen is that 0.39 that's sitting there, when interest goes up by 1 standardized unit, because we're playing with betas, then that 0.39 is going to go up by 0.16. What's 0.39 plus another 0.16? 0.55. Right? This distance is the coefficient for x times z. We can't say that the relationship between income and quality of life is 0.39. You're looking at 2 relationships now between income and quality of life. One says 0.39, one says 0.55. Which one is it? It depends on what? Job interest. When job interest is average, it's 0.39. When job interest is high, as in 1 standard deviation above the mean, it's 0.55. And when it's low, if you went to 2 standard deviations, how much more would this drop? You tell me. 0.16, another 0.16. So then we would be at like in the single digits. And then I would argue that we're probably not different than a flat line at that part. And if you went 3 standard deviations, it will be negative.
Hey, Jess.
There are actually more than 1 slope between income and quality of life. 3. On this drawing, we have what are called 3 simple slopes. Simple slopes are the relationship between a predictor and an outcome at a specific level of your moderator. So what is one simple slope that we have here? Someone tell me all three. I'm not even gonna show you the next slide. Tell me what the three simple slopes we have. Somebody, no, not the numbers. The first simple slope we have is the relationship between income and quality of life when job interest is high. That's simple slope one. What's the other one we have?
The relationship between income and quality of life when job interest is average.
Good. And then the last one is income and quality of life with job interest low. If we just say high, medium, low, these are the three that we have. We have the slope between income and quality of life when job interest is low. Operationalizes 1 standard deviation below the mean. We have the slope between income and quality of life when job interest is average, and we have the slope between income and quality of life when job interest is high. Like good statisticians, though, we're going to test those simple slopes. As we learned in the very beginning, we don't just look at a slope and go, that line is what that line is. We have to test them. And here's how we test them. We can run a simple slopes test. And we can run it standardized we can run it unstandardized or TAs. I fixed the code this year so that we could run them standardized. So here it is unstandardized, here it is standardized. Let's just look at it standardized because nobody wants to deal with unstandardized data anyway. So 0.39, 0.24, and 0.54. They're just rounded by one off. So this is the slope of income when interest is low, the slope of income when interest is average, and the slope of income when interest is high. See that? Now, you see a T and a P value. What does that signal to you?
So
Hypothesis test. So what is that testing? It's testing that slope, that beta. So these are betas against something, against beta equals 0, always against nothing. So it's testing three different hypotheses. It's testing each simple slope. It's testing whether this relationship, let's start with 0.24. So that's this line here, the one I just started. It's testing whether this relationship of 0.24 is significantly different than 0. As in, is it different than a flat line? It is testing each simple slope individually. It's testing whether simple slope 1, simple slope 2, and simple slope 3 are different than a flat line. Why do we care about that? Because it dramatically changes the story. Let me show you an example of why it changes the story. I'm gonna sit for a second and let that can I show you an example of why it changes the story? First of all, here's that same graph. I changed the code slightly. What did I change the code to do? Show the error around it. So remember that we have that coefficient on the top, we have error on the bottom. That's what gives us our t-stat and our p. So in this case, if the error area includes a flat line, which none of these do, then our t wouldn't be significant. In this case, they're all significant, meaning the moderator changes the slope, it changes the relationship between income and quality of life. It doesn't erase any of the relationship. So remember I said there are three types of moderating effects: strengthening, weakening, sometimes called buffering, depending on what we're trying to protect, or antagonistic, meaning or crossover sometimes. I'm going to show you some different examples. I want to start with a buffering example. Usually, weakening and buffering usually mean the same thing. They decrease the strength of an existing relationship. We opt to use the terms differently depending on whether we're weakening something that's good or protecting something that's bad. So think about it. Let's say that I don't have one of these. It's like the one example I don't have. Let's say I'm doing like friendship and self-esteem. Positive or negative relationship? Positive. What about if I use bullying as a moderator? Is that going to weaken that relationship or strengthen it? It's going to weaken it. Am I going to use the word buffer? Bullying buffers the relationship between friendship and self-esteem. No. It's still a weakening moderator. It's going to weaken this relationship. In this case, it's weakening something that we would like to keep strong. So we're just going to use the word weaken. We're not going to use the word buffer. A lot of times when we're doing examples that are weakening hypotheses, as psychologists, we are looking to buffer. We're like, hey, this causes burnout in the workplace. How do we protect people against that? This causes like lack of belonging. How do we protect people against that? Those are buffering hypotheses. So here's an example where financial stress leads to psychological distress. How might we protect people from that? Well, let's arm them with coping skills. So maybe the relationship between financial stress and psychological distress depends on your financial coping skills. If your financial coping skills are high, maybe that relationship gets weaker, i.e. maybe coping skills buffers that relationship. Here's how I would write that hypothesis. Coping skills negatively moderates, meaning it weakens, the relationship between financial stress and psychological distress such that this relationship weakens when coping skills are high. And here's what shows up in the graph. Here's low coping skills. Here's high coping skills. Flatter line for high coping skills, starts lower to begin with, and does not get as psychologically distressed as financial stress goes up. Low coping skills individuals start more distressed to begin with and get more distressed more quickly as financial stress goes up. Again, if you're having trouble, trace each line individually. There's a person at each dot. This person up here is high stress, low coping. Where are they going to be in psychological distress? This person is low stress, low coping. Where do you think their psychological distress will be? Connect those dots. This person's high coping, high stress, and this person's low stress, high coping. That's a really, if you're hypothesizing moderation in your own research and you want to try to really envision what that's actually going to look like and whether you really think you have moderation, draw this. If your lines are parallel, you don't actually think you have moderation. Good test. Now, let me show you what I meant by those simple slopes. Here's another one. The last thing I'm going to do today. Stress and decision-making quality. High stress makes decision quality do what? Go down. The negative relationship. Maybe experience protects that. Maybe if your experience, we can actually protect decision-making quality from the negative impact of stress. So here's my hypothesis. Experience negatively moderates the relationship between stress and decision-making quality, such that that negative effect weakens when experience is high. Here's what the graph looks like. So as stress goes up, decision-making quality goes down. That line for high experience is way flatter. Now, enter simple slopes. Here's the simple slope result. The slope between stress and decision-making quality when experience is high is negative 0.16, P 0.134. What does that mean? That means that line is not significantly different than 0. So what does it mean then if that line is not significantly different than 0? It erases the relationship between stress and decision making. That's why simple slopes is so important, because it's not just that experience reduces the relationship between stress and decision making. It's actually that at high experience, the relationship between stress and decision making goes away. So where does that come in? In your reporting, in your storytelling. Here's the difference. In this one, here's that financial stress, psychological distress coping. As hypothesized, strong coping skills weakened the impact of financial stress on psychological distress. Simple slopes revealed that at low levels of coping skills, that's the blue line, at low levels of coping skills, financial stress was strongly associated with an increase in psychological distress stats. However, at high levels of coping, financial stress was still associated, as in that P was still significant, to a lesser degree. Oops. In the example where the P is not significant, the storytelling changes. Experience weakens the negative relationship between stress and decision-making quality, such that when experience is high, stress no longer impacts decision-making. Much more interesting than straight up multiple regression. Right? I'll take a couple questions, then I gotta go to a chair's meeting. Of effect to error. So your significance can either be a result of the trend or a result of the error. You could say, good, if you wanted to be cautious, what I would do is change this language. So I would say experience weakened the negative relationship between stress and decision-making quality such that when experience was high, the association between stress and decision-making disappeared. That would be a less intense way to word it. I agree with you. That would be stronger. I mean, you have all sorts of clues. You have your standard error term. You have your raw data to look at. You have your homostaticity. You have a million features of your data and results. Remember, the idea is like, why what happened is in your data. So you can go, if you are nervous about whether that's real or not, you have a lot more exploring you can do to figure it out. And you would say, I like the idea of couching the language a little less extreme. And then basically saying, if you don't trust it for certain reasons, and if I were reviewing someone who had a 2 standard deviation, if I were reviewing an article, I would say, hey, it's fine to use 2 standard deviations, but make sure when you're interpreting that you acknowledge like what proportion of a distribution that would impact. Yes, it's those decisions. Generally, what I think about with stats and those types of decisions are like, most decisions are fine as long as you are open about them and you justify their implications. It's about integrity in the justification of those decisions. Moderations are hard to find with small samples because you are looking to find the effect of a moderation above and beyond the main effects. So a lot of times I will see like indicators that there may be a moderation, not statistical significance. And I might say to a student, like, you might need more data. There may be something there, but you need more data. Cool. I made a bunch of examples of different stories of different hypotheses that played with like good things impacting good things and good things impacting bad things and bad things impacting good things. And a bunch of strengthening, buffering. There's a few strengthening ones. And then there's an antagonistic one in here. And I did both the hypotheses for all of them and how you would talk about them in storytelling. So this is a good, like I said, no moderation is the same. So getting good at one is not like I looked at Victor's face when we were looking at one of them and he was like, I'm so confused. And then you'll get to a different one and you'll be like, this one makes perfect sense. And that will happen. So you have to just keep practicing different ones. And I will say that when I had to why? Because your axes, this is your what axis down here? X, that's your Y. We're looking at literally at how the relationship between X and Y changes based on Z, based on that moderator level. So it's set up now graphically such that training is our X and challenge is our moderator. That's critical to understand your model because the interaction term is flippable. So if we write out this equation, y equals 16 point, I'm writing the moderator model here, 16 maybe 0.17 plus 1.54 training plus 2.60 challenge plus 0.76 training times challenge. That moderator term could go either way. That's the change in slope between training and performance for a change in challenge, or it's the change in slope between challenge and performance for a change in training. The only way that's going to make you change the way or inform the way you tell the story is how you set up your theoretical model. So your theoretical model here is really important to the storytelling component. So now the question is, first of all, the first question we always ask is, does the relationship between training, should go here, does the relationship between training and performance change based on challenge? Yeah. Yes or no? How do you know what's the best statistical evidence to tell us? Kayla, the change in R squared between, good. How do we talk about the different models? So I'm going to expand on what Kayla said, get good at the detail. So the change in R squared between model 1, which is what kind of model? What's in model 1? Main effects only. So this line and that line. So we have model 1 was a main effects model only. So here was model 1, training, challenge, both to performance. And a second model, which added in the interaction between training and challenge, explains significantly more variance in performance than the main effects. Therefore, we have an interaction going on. Good. So the answer is yes. We've got our evidence. Now the question is how? So how does training change the relationship, how does challenge change the relationship between training and performance? Let's start with where the relationship between training and performance starts. When challenge is what? Average. That is here. So here we have the relationship between training and performance when challenge is average. Why do we know this is when challenge is average? This is super critical. Centered. It's centered data, which means what are we plugging in this moderator term? We're plugging in a 0 for challenge, meaning the moderator term, the change in slope, doesn't impact anything. It stays at 1.54. So here is 1.54. That's the slope between training and performance when challenge is average. Now we can look at the change in slope. When challenge goes up by 1 point, what happens to the relationship between training and performance? Let me say that again. When challenge goes up by 1 point, what happens to the relationship between training and performance?
Increase by 0.76.
Good. It increases by 0.76. That's a change in slope. So starting slope is 1.54. And as challenge goes up, I literally like to think about it as a bump. So if this is training, here's its nice little 1.54. It's sitting there. In comes challenge and it's change, and it hits that 1.54 and changes it by this much. So that 0.76 gets added on to 1.54. What happens if challenge goes down by 1 point? Gonna go down by 0.76. Now, 1 point changes aren't very helpful to visualize. So in the graph, we don't have 1 point changes, we have 1 standard deviation changes. So here we have the graph. This is when challenge is what? Low, 1 standard deviation below. Here's when challenge is high. Now, the question is, what are these slopes? We can look at it and we can see it looks when challenge is low, the relationship between training and performance is actually negative. So when you're in a training and it's really dull and not hard, then actually training has a negative impact on performance. When you're in a challenging training, then the more training you get, the better you get at your job. As long as that training is what? Challenging. The question though is, do we know whether these slopes are significant or not? From the graph, no. From the simple slopes, we do. And what do we see? At high challenge and low challenge, they are. At average challenge, there's no relationship. These are significant. This is not. I wouldn't expect this one to be. So I think the simple slopes output is. So when challenge is average, there's no relationship between training and performance. Right? Make sense? So in general, sometimes training and performance works, sometimes it doesn't. It depends on what? How hard it is. So when the training is hard, performance goes up with more training. When training is low, or when challenge is low, performance goes down with more training. Now, here's a very important trap that people fall into. They say, oh, performance goes up when it's harder. What is that? That's a main effect of challenge. This is changing the relationship between training and performance. As training goes up, what happens to performance when challenge is high? When you are describing a moderator effect, make sure you have both the X and the Y in your storytelling. If you say the moderator and the outcome, you're actually looking at the main effect. That's a pitfall I see a lot. Talking it's a moderation, you're actually talking about a main effect. Cool, we're gonna do more. Today is Categorically Depends. It's a cog speaker that really cuts across all of the different disciplines. And she's talking about how thinking about the future actually changes current behavior. Literature suggests that income is a predictor of quality of life. We looked at this last time. Cool. Except you think this might depend on industry. So our research question in Statsy language would be, does industry moderate the relationship between income and quality of life? What would it be in less Statsy language? What's my favorite non-Statsy moderation word? So what would it be? Does relationship with income and quality of life depend on industry? So remember, a reminder when we fit moderation models, this is our theoretical model. We've got a relationship between income and quality of life that exists as if we're not considering industry. We actually think that that line, that slope is going to change depending on what industry people work in. That's why that industry is coming in and hitting that slope. It's literally hitting it and changing its magnitude, its beta. Statistically though, we can't regress things onto lines. So we are going to run it this. We've got income, main effect of income, main effect of industry, and then the interaction. And we always run the main effect of the moderator. It's maybe not in our theoretical model. It could be. It might not be. We always run it in our stats model because we want to know if our interaction explains additional variance above and beyond the main effects of our two predictors. We know our general structure of our model. It's no different with a categorical variable versus a continuous variable. What's the only difference? What are we going to have to do? Dummy code. it's gonna end up impacting our interpretation a little bit. This is, I think, where it gets a little bit complicated, the word, to be careful. There are a lot of pieces. There's a better word. I'll think of it. Here's our raw data. We've got our employee number on the left. We've got income. We've got quality of life scores, and then we have industry. So we've got 3 industries: technology, agriculture, and government. What's the first thing we have to do if we're going to run a moderation to our data? Center our data. What predictors are we centering here? Income. First of all, we're going to center income. First of all, we can't center industry yet because we don't have numbers. There's nothing to center. So first thing I'm going to do is I'm going to center my income. Another review of centering, because understanding centering is super key. Let's zoom in on someone. This person's centered income is 4.32. What does that mean? What do they make? 4.32 above the average, whatever that is. Good. What does this person make? 6.6 below the average, whatever that is. If someone had a perfect 0 in here, what does that mean they make? The average. That becomes critical because when we plug in zeros, what are we really plugging in for income? Average income. That's starting to make more sense now. I can see it getting quicker. We've got 3 levels of our categorical variable. So we need how many dummy codes? 2. Here they are. I'm going to call them J1, job 1, and job 2. First one is the shift from agriculture to technology. Second one is the shift from agriculture to government. So what's my reference group? Ag. Good. So remember, these 2 together, 2 variables, 1 construct. Can't ever divorce them. 1 construct, 2 actual variable terms in the model. Create a moderator term. Now, to create a moderator term, you multiply predictor 1 by your moderator. So we have to do that. We have to multiply income centered by industry. But how many industries do we have? 2 variables. So same thing with our moderator. So we have to multiply income by J1 and income by J2. We never center the outcome. We don't want to center the outcome because then we're predicting centered outcome values, not actual values of Y. It would mean that the Y axis wouldn't give you if you were trying to predict a value, you'd be predicting centered Y values. All right, here's our equation. Let's look at the different pieces. This is why I color coded, because you actually still only have 3 pieces. You did with continuous. It's that each piece has more than 1 term in it. So let's look at these. You've got the pink, which is still, is there a main effect of income on quality of life? Then you've got the green, that's what? Main effect of industry on quality of life. And then you've got the red, and that's what? The interaction. Good. How do we talk about the interaction? Well, do income and industry interact to affect quality of life? Or let's be more specific here. This is the generic math version. I want us to get better at the storytelling. And in order to get better at the storytelling, we can't be, that's the interaction. We have to actually contextualize what the interaction is. We can't contextualize the interaction without a what? Theoretical model. So there's our theoretical model. Industry is operating as our moderator, which means this term is actually saying, does the relationship between income and quality of life change based on industry? See how that's different than saying, do they interact? Yes, are we clear on that? It's contextualize versus decontextualize. The more you can practice contextualizing that way, the easier storytelling gets at the end. Questions about this? Questions online? So model fit looks exactly the same. Here I ran 2 models. What's in my first one? Main effects. What's in my second one? Main effects and the interaction. So we've got model 1, 79% of the variance in quality of life explained. Model 2, 82% of the variance change is an additional 4%. That change is significantly more. So here's how I talked about it. Oops, not that. Model 1, which tested the main effect of income and industry, was significant, explaining 63% of the variance in quality of life. Model 2, which included the interaction between income and industry, explained significantly more variance, suggesting that the association between income and quality of life varies by industry. Notice that last sentence is written in a very specific way. How did I write it? It's in line with something. What? My research question and my theoretical model. I could have, it would have been accurate to say suggesting that income and industry interact to affect quality of life. That would have been factually accurate. That does not theoretically align to the fact that I'm conceptualizing industry as my moderator and income as my predictor. I'm purposefully talking about it in alignment to my research question and my model. That makes sense? It's not wrong to say they interact. Statistically, that's accurate. I'm storytelling always along the way in alignment to the research question, which is, does the effect of income on quality of life depend on industry? All right, starting with this blue box, that is the what? The intercept. So if we knew nothing about anything and we regurgitate memoried, the intercept is the predicted quality of life when all values are 0. Cool? All right. So plugging zero into every variable means something different for continuous and categorical variables. Let's start with continuous. What does it mean to plug in a 0 that's centered for income? Average income. Good. What does it mean to plug in all zeros for a categorical variable? Good. So what is this number actually? It's the predicted quality of life for someone with average income who works in agriculture. See, you can think your way to it. Now, let's think our way to it visually and with the equation. Ready? Here's our graph. We're going to graph it. We're going to graph every value after looking at the value. So here's our graph. I made a little reminder that the 0 is actually x-centered equals 0, which means it's average income. So here's our equation, and I plugged in zeros for every variable. Cool? So 2 things to remember. Remember that a centered value of 0 equals average income. And, whoa, it's the reference group. So what is the only thing we're left with? 74.58. That is the intercept for the agriculture group. Got it? Ready for the next one? Pink. Ready for the next one? All right. How do we interpret this if we were robots? This is the slope between income and quality of life when the other variable is average. Remember, it's a moderation, so it's not holding constant. It's when the other variable is 0, has to be, because otherwise the moderator term is going to change it. So let's do that. The slope between income and quality of life when industry equals 0. Wait, industry equals 0, which is average, is not a thing if it's categorical. So it's when it's agriculture, the reference group. So this is the slope between income of quality of life for those in the reference group, agriculture. Let me show you why that is with the equation. Here's that 0.26. I put in zeros for everything else. What happens to all of these terms? They go away. So 0.26 is the slope between income and quality of life only when we plug in zeros here. And what does it mean to plug in zeros here? Reference group. So that's the slope between income and quality of life for the reference group. Looks that. You can do B of 0.26 or beta of 0.30. As I said before, I much prefer dealing with betas when it comes to slope because I can visualize it. But I put them both on there so we don't forget they're the same thing. Cool? We've got J1, unstandardized 5.28, standardized 0.575. Here's where it gets fun. How do we literally interpret this if we were robots? The same thing we always. For a 1-point increase in J1, we can expect a 5.285 unstandardized increase in quality of life, assuming income is 0. Cool. A lot of the things I said don't contextually mean anything. So first of all, what does a 1-point increase in J1 mean? From reference group, which is 0, to a 1 in J1, which is technology. Then we can expect a 5.285 unstandardized increase in quality of life, assuming income is 0. What does income of 0 mean? Average. So I'm going to actually go backwards here. Watch what happens here. Only happens with categorical variables. I plug a 1 into J1. What does this term become? A constant, a number. It's not a slope, it's a number. So where can it go? It can only get added to the intercept. So watch what happens. 5.29, you end up with an intercept, a starting point that is higher than agriculture started. And it looks that. Tech starts 5.29 points above agriculture. So going back to the last slide, it's actually a change in intercept from agriculture to technology. Individuals with average income in tech are predicted to be 5.285 points higher in quality of life than ag workers with average income. So remember, here we have average income. So if you're somebody here if you are saying, I've got people who make average money in their industry, if they're an ag worker, they're predicted to be here. And if they're a tech worker, they're predicted to be 5.29 points higher. Average across all industries. And you know that. You can tell me why. Exactly. Because we centered with one mean. Yeah, it's not group centered, it's grand mean centered. You can in other types of analysis. Second one, same exact concept here. We could interpret it as for 1 point increase in J2, we can expect a 10.05 unstandardized increase, assuming income is 0. That's the literal interpretation. What that really means is it's a change in the intercept again. The quality of life for individuals in government who make average income is predicted to be 10.05 points higher than agriculture workers with average income. Let's look at how that happens. So here we plugged in a 1 for J2. What does that become? A constant. This term doesn't get applied because it's a 0. They're a 0, 1. They're a gov worker. 10.5 gets applied to the intercept with a starting intercept of 85.08 for gov workers. They start here. Now, I'm going to start with the literal interpretation and then get to how do we contextualize that. So we know that moderator terms are what? They're not slopes, they're change in slopes. So all moderator coefficients are changes in slopes. Cool? So here's how we would interpret it. Now, remember that moderator terms are interchangeable. They're income times J1 or J1 times income. So I have to decide when I'm interpreting whether I'm going to say for a 1 unit increase in income, this is how the relationship between J1 and quality of life would change, or for a 1 unit increase in J1. How am I going to choose? Model and research question. Which of the things, predictor or moderator, is the one I want to refer to as the 1 unit change? The moderator. I'm interested in what happens to the core relationship as the moderator goes up or down. So I always want to say, as the moderator increases, this is how the slope changes. So here, as J1, if I were going to interpret this literally, it would be for a 1 unit increase in J1, we'd predict the slope between income and quality of life to go down by 0.38 unstandardized or 0.28 standardized. Cool? Everybody get that part? Questions about that part before I go to conceptual. So now let's actually look at it, what happens. Let's start with conceptual, unstandardized, and we'll do standardized. So this is the change in slope between income and quality of life as we move from ag to tech. So we've got income, quality of life, and we're seeing how much is happening. How much is that original slope here in yellow changing when we move from a reference group to J1, which is tech. Now, well, we have to know, well, where are we starting? So what's the unstandardized relationship between income and quality of life for the reference group? 0.26. Y'all see it here? And what is it standardized? 0.30. So that's where we start. The unstandardized slope between income and quality of life for the reference group is 0.26. When you move to tech, that 0.26 goes down by 0.38. That leaves us with an unstandardized slope of negative 0.12 for the tech group. We can do the exact same thing standardized. Starting standardized slope between income and quality of life for the reference group is 0.3. When you move to tech, so you go up 1 unit in J1, that 0.3 decreases by 0.28. That results in a standardized slope of 0.02 for the technology group. Let's look at what that looks on the graph. I'm going to use the betas here because they're easier to visualize. So I'm plugging in a 1 for J1 in my moderator. Why? What does that represent? Yes, what does that represent in the interpretation of a moderator term? That's my 1 unit increase in J1. So for a 1 unit increase in J1, this resulting term is going to be negative 0.28 what? What does this term become if you simplify this whole thing here? Do you know how to multiply 1 by 1? We know how to multiply by 1. Negative 0.28 income. It's a variable. It doesn't go away. So if we have 0.3 income over here and negative 0.28 income over here, we can combine those terms and look what happens. 0.30 income minus 0.28 income, and we're left with a slope of 0.02. There's the slope for tech, okay? So it's negative 0.12 unstandardized, 0.02 standardized. Good so far? I told you, nuance, just a lot of pieces, thinkable. Plug your ones or your zeros. Good, that's a good question. So a couple people have asked now about, oh, this is these intercepts are the predicted quality of life when income is average for each of these three groups. The income is average is global average. Yes, that's informing the whole equation. That's not our focus. That's not our research question. Our research question is what's the relationship between income and quality of life for each of these groups? So it's not the fact that we global mean average is and that we have three intercepts is giving us the correct equation. It's not our focal question. What does that mean? Well, they're totally different units. So it doesn't matter that they're in, no. And especially not when what? What do you suppose about this line here? Exactly. So we've got tech, last line. Here's the last one. This is another moderator term, so it's a change in slope. So if we want to literally interpret this, we would say for a 1 unit change in our moderator, which is J2 here, we'd predict the slope between income and quality of life to go down by 0.54 unstandardized or 0.29 standardized. So we're starting again, still at 0.26. That's that starting for the reference group. When you move to government, that 0.26 goes down by 0.54, which results in an unstandardized slope of negative 0.28, okay? Standardized, we started at 0.3. When you move to government, that 0.3 decreases by 0.29, which results in an unstandardized slope of 0.01. So same concept, we plugged a 1 in for our moderator J2. We end up with negative 0.29 income. We can combine it with our starting slope and we end up with 0.01 income. Or if we did it up here, we did 0.54 income and we added it minus 0.54 income here, we would get minus 0.28 income. And there it is. Why are they so different? Because the standard deviations are different of the raw data. If you look at the way the data were measured, they weren't measured in the same units. So 0.28 looks wildly different from 0.12. They're actually not wildly different because they're in wildly different units. That's why we care about betas and not these. One was measured in 110, one was measured in 1 to 100. So here we are with our 3 lines. There's not really, I can ask, are there questions? It's sort of one of those ones where you have to go through it a few times to be like, yes, I get how that changed the intercept. I get how that changed the slope. We're going to do this exact same example from a different perspective, which is the equations. Sometimes people get it from doing coefficients to graphs. Some people get it by the equations. We're going to do both. Quality of life is going to go, for every 1 standard deviation increase in income, quality of life is going to go up by 0.01 standard deviations, which is really small. As we go up by 1 standard deviation, quality of life is going up by a tenth of, not even a tenth of a standard deviation, tiny, which is why the line is virtually what? Flat. So here are our equations. We're going to look at these equations again in a different form. We've got 3 different intercepts with 3 different slopes. We also look at the standardized equations. When we're talking about the reference group, there's no intercept. Remember we had those J1 and J2 here, even in the beta version, even in the standardized version. So in these standardized versions, we still have changes in intercept. What do those mean? They're standardized values also. So for the government group, what does a 0.9 intercept mean? It's almost they start almost 1 standard deviation above where ag starts. Exactly. Again, not our focal question. When you're looking at that and going, what does that mean? That's what that means. So here's a question. What's a simple slope in the context of this research? Let's start with that question. What is a simple slope? What's a simple slope here? First of all, how many do we have? 3 simple slopes. What is one of the simple slopes? The relationship, say it loud. When you are describing a simple slope, it should start with the relationship between a predictor and an outcome, and it should be what? At a certain level of your moderator. When you're dummy coding, it's going to be what, or categorical moderator, it's going to be one of your levels. When it's a continuous moderator, it's going to be when that moderator is high or low. Do you think the simple slopes analysis would reveal significant slopes here?
One.
For which one? My hunch here is that the slope between income and quality of life for agriculture, so the yellow line, would probably be significant and positive. 0.30 slope. So for agriculture workers, as income goes up, your quality of life increases. For tech workers and government workers, it seems to be flat. You do need to look, you can also look at how high they are. So what's interesting is, as you make more money as an ag worker, your quality of life goes up to a point where you actually meet the quality of life of government workers. Potentially exceed, we don't know how far income goes. Is your model. Got it? That's your model. You can figure out all of the things you need to figure out by manipulating this model. So here we go. We're going to start with it. We're going to do unstandardized and standardized. For agriculture workers, let's start here. Here's the whole equation. What does it mean to be an agriculture worker? What's your dummy code? 0, 0. So what am I going to do? I'm going to plug in zeros for J1, and I'm going to plug in zeros for J2. This is going to be one of those ones where you want to follow along rather than note take, because I'm going to cross out things as I go. So I've plugged in 0 for everything. Agriculture workers, so they get a 0, a 0, a 0, a 0. So that whole thing goes away. What am I left with? An intercept and a slope. That's the whole equation. Now, let's do it for tech workers. What am I going to do for tech workers? Plug in a 1 everywhere I see what? J1. Here's 1 and here's 1. First thing that happens, those two things go away. Then I end up with this 74.58 plus 0.26 income plus 5.29 minus 0.38 income. I've got two numbers. Here's a number, and I've got two slopes of income. Cool. I can combine the yellow and I can combine the blue. And I end up with one intercept, one slope. Okay? Same thing for government workers. Start with the whole thing. Plug in a 1 every time you see J2. Get rid of the terms that go away. Anytime you multiply 0, everything goes away. You end up again with two numbers and two slopes of the same XY relationship. So combine the terms, yellow goes together, blue goes together, and you get the equation for government workers. What's the difference? So here's the slope is 0.26. Here it's negative 0.12, and here it's negative 0.28. The difference between these two is the moderator term. 0.38. The difference between these two is the moderator term, 0.54. Those are the changes in slope from the reference group. So now, if you want to put it all together, cool idea, this first part is always going to be the reference group stuff, because everything else has what in it? What does it have? It's got dummy codes in it. J1, J2, J1, J2. So if we're talking about the reference group, all those terms are going to go away. So in a dummy coded moderation model, in a categorical moderation, that first intercept and slope is always going to belong to the reference group. These next two that belong to the dummy code, they're going to change the intercept. And the last one, the red, that's going to change the slope. Cool. You do the exact same thing if you want with the standardized version. For ag workers, you put zeros in for everything. Guess what? You end up with 0.3 income. That's it. Now, why do I have Y standardized? Because you're predicting standardized values of Y now, not predicting raw values of Y. You do the same thing for tech. You put a 1 in to represent tech. You can combine these two. Now you have a new thing. You have a number for the first time. So you get 0.58 plus 0.02 income. Same thing for gov. Plug in a 1 for gov. Cross out your zeros that go away. Here you have two slopes of income. One is the original, one is the change. And you have a number value, and you're left with a standardized equation. Same idea. First part belongs to the reference group. Second part changes the intercept. Third part changes the slope. What's our interpretation? Industry does moderate the relationship between income and quality of life. There seems to be no relationship between income and quality of life for tech and government workers, a significant positive relationship between income and quality of life for ag. Or you could say the relationship between income and quality of life depends on industry. For ag workers, the more money you make, the better quality of life. For tech and government workers, there seems to be little effect on quality of life. If you wanted to add more of the story of like where people start relative to each other, you totally could.
Can we go back to slide 25? So for standardized
Can you tell
equation,
me what slide? Oh, hold on, I can go.
standardized
Yeah,
equation. So if we were to graph the first one, would my y-intercept be down at 0, 0?
If you're no, it would be more that this axis would change. So the lines wouldn't change. What would change, and the points wouldn't change. What would change is that this point would be 0, and this would be plus 0.5 SD plus 1 SD minus 0.5 SD minus 1 SD. The scaling of the axis would change.
Oh.
This B is equivalent to this beta. The negative 0.28 is the raw value, and this is the standardized value. Because it's not significantly different than 0, that's why you're seeing the sign change. You wouldn't see the sign change if the slope was significant. Because if the slope were significant, meaning it was actually going up, because what we're testing when we test simple slopes is whether this B or beta, so the null hypothesis in a simple slope, is whether this simple slope is significantly different than 0. And given a beta of 0.01, it's not going to be significant. Good. We don't have the actual data to support it here. It's so flat, I can virtually guarantee it's not going to be significant. And that negative versus positive difference between the B and the beta also suggests not different. The other thing to think about, Ray and JJ, is that remember that in the unstandardized version, you have this giant 74.58 that's getting added to get your predicted Y. So even though you have a negative slope here that you're starting with, that's part of the offset too. Let's level up. There's one of these on your DAs. This is an educational researcher replicated a portion of a study examining how SAT predicts University of California GPA based on various demographics. In their examination of family ed background, they examined first-generation college students, dummy-coded 1, versus non-first-gen students, dummy-coded 0. Using the following information, create the regression equation predicting UC GPA from SAT scores as moderated by family educational background or first-gen status. You're working backwards here. You don't have coefficients. You got to make the coefficients. So what's the very first thing I'm going to do here? Probably. What? Draw a model, because I want to orient myself around what's my predictor, what's my moderator. So what's my outcome? That's easy. First, I'm going to label my reference group just so I remember. Non-first gen is my reference group. Then I'm going to draw my model. GPA is my outcome. SAT is my predictor as moderated by first gen status. So my research question is, does the relationship between SAT and GPA depend on whether somebody is a first gen student or not a first gen student? Good so far? What would be the next helpful thing to do? Draw the skeleton of the equation. You're going to have to end up with an equation, so we might as well remember what terms have to go in there. What are we going to have to figure out? Well, we know we have an intercept. We're going to have a slope here. We're going to have a slope here. And we're going to have what? A moderator, a change in slope. Now, how many levels of our categorical do we have? How many levels of our categorical do we have? 2. So do we need 2 dummy coding terms? No, this one's a little easier. We only need 1. So we're going to have an intercept, which is average GPA. So how many terms is this equation going to have? You can count 4. Here's our standard equation. Our standard equation is y equals intercept plus b1x, b2z, b3, x times z. There's our skeleton. Now all I'm going to do is swap my x and z's for my actual variables here. What's my x? SAT score. What's my z? First generation. Great. So there's my equation. Good so far? This is all set up to orient myself. It's not the hard part. Now let's do the fun part. So there's the equation that I came up with. And somehow we have to do what? We have to put coefficients in for B1, B0, B2, and B3. So let's start with what would happen. So non-first gen is the reference group, so they're coded 0, and first gen is coded 1. So if we plugged in a 0 everywhere we saw FGS, that would represent non-first gen students. See that? And what would be left? Just this part. So B sub O would be their predicted GPA, when SAT was average. And what would B1 be? The slope between SAT and GPA for who? For who? For the reference group, non-first gen. Do we have both of those pieces of information?
Yeah.
Yes. So we have the first part of the equation. Y equals 3.20 plus 0.37 SAT. Because this is what it would look like if we plugged in a 0 for FGS, signaling the first gen group. Now we have to figure out B2 and B3. So what do we actually need to find? We need to find the change in intercept. So how do we get from 3.2? How do we get from 3.2 to 3? Subtract 0.2. So then we've got y equals 3.20 plus 0.37 SAT minus 0.20 FGS. And then how do we get from 0.37, which is the slope for first gen, non-first gen, how do we get from there to negative 0.10? How do we get there? Subtract what? 0.47. Here's your equation. So this is the information for the first gen. This is the line for non-first gen. This is the line for first gen. The single equation has to give us the change in the intercept and the change in the slope. How does it do that? Well, we went through the 3 parts. When we have a categorical predictor, this is the change in the intercept, and this is the change in the slope. Cool? You get to practice one of those on your DA.
Conceptually, would this then say that for first generation students, SAT is either not related, because we don't know the significance level, or negatively related?
Negative 0.10 were not significant, then it would mean for first gen students, there's no relationship between SAT and GPA, which is what I would suspect. So here's our continuous moderation. It's gonna follow exactly what we did. The code for our models is gonna be exactly the same. Our assumptions are gonna be exactly the same. The only code that's gonna be new is creating a moderator term. That's new, and graphing and doing the simple slopes. That's it. Everything else is old code. It's multiple regression code. So you are a positive social psychologist studying the effect of burnout on positive coping strategies. So burnout is our predictor, positive coping outcome. Your past research demonstrates that more burned out an individual is, the less they're able to exhibit positive coping strategies in the face of challenge. However, you've noticed that this isn't a consistent reaction. Some individuals seem to be more resistant to burnout's impact than others. You have a suspicion that personality, specifically extroversion, may play a role in this difference. You decide to test this hypothesis. So what's our moderator? It's extroversion specifically. So we're not looking at, this is not a categorical. We're not looking at introvert versus extrovert. We're looking at level of extroversion. And we're looking at whether the level of extroversion moderates or changes the relationship between burnout and positive coping. I'm reading in the data. Notice it says DTA. You see that? And then I'm making all of my column names lower because that makes my life easier. So here's our data. We've got extroversion, neuroticism. You could test the moderating effects of neuroticism. This would be a great data set to now go run a couple other moderations by yourself for fun to practice. You've got other moderator models in here you could run. You've got neuroticism, you've got burnout, you've got positive coping, you've got negative coping, and you've got anxiety. You've got a bunch of different variables in here that you could practice moderated models with. What else do you notice in here that's kind of annoying? Missing data. That's gonna mess with our model. I'm gonna run my descriptives, and what I notice here, I've got missing data. It's not a lot, and look at my N. Do you see that? That's huge. So I'm just gonna get rid of them. I'm gonna list-wise delete them. NA.omit means get rid of any lines that has missing data. So go ahead and get rid of it, and I'm gonna rename a new data set. For the sake of time, I'm gonna skip our assumptions because they are the exact same code that we have been running for simple regression and multiple regression. Scatter plots between your predictors and outcomes, correlation tables, homoscedasticity, fitted residual plot, Roush-Pagan test, multivariate normality. That's it. Same as always. Got it? All right, now let's prep. What do we have to do to prep? Center our continuous predictors. Both of our predictors are continuous here, extroversion and burnout. So here's how we center. We take our variable, we subtract the mean of that variable, and then You see this here? rm.na equals true. We actually don't need that because we don't have any missing data. If we did, we could use this term to be when you're calculating the mean, skip over missing data. We don't really need it. It's going to give us the same result here because we don't have any missing data. And I usually name my variables burn.c and extra.c so we remember they're centered. And those are going to go at the end of my data set. Burn.c, extra.c. What's the next thing I need to do? Everybody, what do I have to do next? Create a moderator. I'm doing moderation. So how do I do moderator term? I literally multiply my two centered variables. So I've got burnout predicting positive coping, and I've got extroversion moderating. So I need to create a third term, which is burnout times extroversion. Okay. How do I do that? Very simple. I say create a variable. That's $ means variable. I'm going to call it mod. That's not very exciting. It'll work. And what do I want to make it? I want to make it that variable times that variable. It's a very simple operation. That asterisk is the R symbol for multiply. Question. Run it, and you have this mod term over here. Why is it all weird numbers? Because everything's centered and because they were weird values. All right, now what are we gonna do? Are we ready? What do we have to do? Hello?
Create your models.
Yeah, create our models. Guys, wake up. We only have 10 minutes. Come on. We gotta specify our models. So let's start over. We've got a model. Burnout on positive coping, moderated by extroversion. What's our research question? Does the relationship between burnout and positive coping depend on extroversion? We read in the data, we checked our assumptions, theoretically. We centered both predictors. We created a moderator term. What else is there to do? Run the models. So what's our first model going to be? Main effects. So here we have the same exact code we've used for multiple regression, linreg. Dependent variable is pos cope. We're going to use burnout, extroversion in our moderator term. First model has burnout and extroversion in it. That's our made effects model. Second model is going to add moderation on top of that. I'm going to test those models together, and that's it. Let's run it. Here's model 1. It explains about 12% of the variance. So the main effects explain 12%. Main effects and the modder explain 13%. It's not a huge change. It's significant. So in this case, we can actually, in a multiple regression, we often to look at all the models, even though there's a best model, because we want to see how things change. Here, we're really looking at main effects versus moderation. So we can go ahead and go look at our moderation level here. And what do we see? The very first thing that I'm going to do here, almost always, y'all, this is what I would do if this were my own data, is I'm going to put these betas on a figure and annotate, because that is the easiest way for me to figure out what's going on. And I'm not telling you that, oh, you should do this, but this is literally what I do with my data. I'm literally going to take my betas and I'm going to annotate this. So the relationship between burnout and positive coping when extroversion is average is -0.34, p less than 0.001. So as burnout goes up, positive coping goes down when extroversion is held average. That's the main effect. For extroversion, the beta is 0.09 and the p is less than 0.001. So as extroversion goes up, positive coping goes up a little bit as long as burnout is average. Now let's look at that change in slope. Extroversion, the change in slope is 0.11 and the p is less than 0.001. So as extroversion goes up, it's going to come in and hit this starting slope. As extroversion goes up by 1 standard deviation, it's going to come in and it's going to change the slope by positive 0.11. So when extroversion is average, burnout to positive coping is -0.34. When extroversion goes up 1 SD, the relationship between burnout and positive coping changes by that positive 0.11. And we get what? 0.23, -0.23. So what happens when extroversion goes up? So what happens to the slope when extroversion goes up? It decreases. It gets weaker. It gets weaker. That's a buffering effect. Because we're talking about the effect of something bad on something good, we're like, oh, this bad thing hurts this good thing, -0.34. It hurts it less when extroversion is high. Now, let's look look at what that looks graphed. If you're having trouble with R with packages, follow along because you'll miss the actual learning part over the tech part. So we can run them two ways. You can run them unstandardized if you want to know the unstandardized simple slopes, not super helpful. Or if you want to know what the slope is between burnout and positive coping when extroversion is high and low, you want betas, you can run it standardized. Here are the two ways to do that. This is new, wasn't in last year's if you want to run them with betas instead. We're going to use the same code with one different addition for standardized. The first one is unstandardized. You're going to need these three packages. Again, if you don't have them, I would watch, take notes, and do it later. The first thing you have to do is fit the model. You can use your raw variables. You don't have to use your centered ones. Linear model, pause coping is the outcome, regressed on, burnout times extroversion. Do you see that? Why don't I have to have the main effects in there? Because linear models know that when you have an interaction, you also need to include the main effects. It's automatic. Also, we're going to be looking at simple slopes, so it's going to model the simple slopes for us. The model I'm calling it is model.pauseComp. Then I'm going to run the function simSlopes on that model, and I'm going to give you the predictor and the moderator. So this is where I'm theoretically identifying. This is where I'm doing the theoretical work. This does not tell simple slopes which one's functioning as the predictor and which one's the moderator. This is. I'm telling it which one's my predictor, which one's my moderator. I also want it visual. So I'm going to use the function interact plot and I'm going to predict it. Okay. Here's our outcome graph. So you can see here's the mean and exactly what I showed you on the notability on the iPad. When extroversion is high, it's still a negative slope. It's not as steep. You see that? That solid line. The question is, are they all negative? So if they were all negative, what would that mean? Extroversion can make burnout have less of an effect. It does not completely erase the effect. It doesn't make it flat. So we can look at our simple slopes. Here they are. It's very nice. So this is it when extroversion is low, when extroversion is average, and when extroversion is high. And what we can see is they are all significant, meaning they're all negative. Be very careful. These are not standardized. Those are Bs, not betas. Okay. JJ, to your very earlier point, that negative 0.22 matches the negative 0.22 in the regression coefficient table. Okay. Now, if we want them standardized, we have to add one line of code. Here's that same model. You don't actually have to run it again because we already ran it. I added one line here, which is standardize the model. So after I generated the model, I standardized the model. That's going to mean that every coefficient that pops up is automatically already standardized. Two things will be different. Instead of betas, you'll have, or instead of Bs, you'll have betas, and the axes on your graph will be different. They'll be in standard deviations instead of raw values. That's it.
Why does it not matter that we don't center when we're talking about simple slopes?
Because it's still going to run, it's running the interaction. It's not predicting actual values. It won't be any different.
Okay.
You can run it with center. It'll be the same graph.
Okay.
You guys want to see a categorical one? If you have to go, you can go. I'll do a categorical one. Categorical. All right. Recent studies suggest impulsive individuals may be more vulnerable to cognitive interference from external or internal distractions. This might be me research. This can overload working memory capacity, making it difficult to process and retain information. However, less is known about which types of cognitive interference is liable to moderate this impulsivity effect. This study tested whether smartphone availability moderates the effect of individual differences in impulsivity traits, both positive urgency and negative urgency. So positive urgency with your phone is the idea of, so Heather has her phone on the table, you all do. Heather has her phone on the table. Positive urgency is you're missing out, exactly. Negative impulsivity is what's wrong, what's happening. So both types of impulsivity. We designed an experiment in which 132 college students completed a lab task that assessed visual working memory in 3 conditions. 2 conditions differed in terms of smartphone availability. So smartphone turned off on the table was group 1. Smartphone in silent mode and on the table was group 2. And then condition where the smartphone was not available at all, there was a calculator on the table. So that's the control condition. And the idea is let's still put something on the table. So you want to make it as close to your treatment conditions as you can. It's not your phone. Okay? This is another one where you can practice the moderation on your own because I've got 2 in here. I've got positive impulsivity and negative impulsivity. We'll do one now. We're going to read in the data. So we've got group, so cell phone off, cell phone on silent or control, which I think is called calculator. You've got their subject ID. You've got K, which I think is their working memory. You've got SPAY, which is their smartphone addiction inventory score. So they controlled for how addicted you are to begin with on your smartphone. You've got negative and positive impulsivity. Now, we need to dummy code our groups. So we've got off, silent, and calculator. What's a good reference group here? Control. So we're gonna make our control group calculator 0, 0. And then for the off group, I'm gonna call it condition off so I remember what it is. So it's the difference between calculator and off. And then I'm gonna call my other one condition silent. It's the difference between calculator and silent. So this is our in-class example where we have a dummy coded moderator. It's got 3 levels. So we actually need 2 dummy codes. That you draw this model, not theoretically, also statistically. So if you look theoretically, we're talking about positive impulsivity on working memory moderated by smartphone condition. Because we had to dummy code stuff, our stat model is a lot more complicated. We actually have positive impulsivity on working memory. And then how did we conceptualize or operationalize smartphone condition?
Later off.
We dummy coded it. Our actual variables in our data set are dummy coded. So we've got condition off and condition silent. And both of these have main effects. You also always have an intercept, B. So you can see here, 1, 2, 3, 4, 5, 6. That's how many coefficients you're gonna get in your output. Or if they're betas, how many are you gonna get? 5. There's no original intercept for the reference group. So draw these because you should be able, once you can go from, I think one of the most helpful things is being able to go from the coefficient table to this, to the equation and back. I find labeling much more helpful than doing equation and coefficient table. We have to center our continuous predictors. I'm centering all 3 here in the demo, not because we're using all 3 in our model, but because in case you want to play with the other 2, you can. So positive impulsivity, negative impulsivity, and smartphone addiction, we're centering. There are our centered predictors. And now what do we need to do? Create a moderator term. We got to multiply our centered predictor by our dummy code. You got to moderate, have your theoretical model next to you. You've got to moderate positive impulsivity by smartphone. Where's smartphone in your data? It's here, 1s and 0s. Here it is for the positive impulsivity. So conditions times positive. And here it is for negative. And then we're ready. We were in the other one. Dependent variables, that's working memory. Here are covariates. It looks a lot. Remember in the PowerPoint, 3 colors, intercepts, or sorry, 4 colors, three terms, main effect, interaction. You have it here. Main effect of positive impulsivity, main effect of condition, interaction. So the first model's got my main effects. Main effect of positive impulsivity, main effect of smartphone condition. Second one adds in my moderation. And here's our model fit. 6% with main effects only, 11% with the moderator, 5 additional percent variance in working memory, significant difference. So there is a moderation. Let's look at what you can assume is that the slopes are going to change. At least one of those slopes is different than when we're talking about a calculator. It changes. It means that the moderation is significant. It is changing when you change smartphone condition. So let's look down here. Here we've got our slope between positive impulsivity and working memory. So as positive impulsivity goes up, what happens to working memory? It goes down, except no, it doesn't. There's no relationship. Look at that p-value. So when there's a calculator on the desk, there's no relationship between positive impulsivity and working memory. Interesting. Why might that be? Well, maybe because I don't have anything to be impulsive about. Then we have our change in intercepts. And then here we have our moderation. So this one's kind of cool. When we move from calculator to off, so instead of having a calculator on my desk, I have a phone that's off. Meaning I know that I cannot read anything on that phone. Does the relationship between my positive impulsivity and my working memory change? No. Why not? It's not significant. Look, that's not a significant change. It's gonna go from negative 0.07 to positive 0.03, and that's not a significant change. That also makes sense. I still can't access anything if I have a phone that's off. Now let's check what happens when my phone is on. It's silent. What happens when my phone is on? It's silent. So when my phone is on silent compared to a calculator, the relationship between positive impulsivity and working memory is going to change. And in fact, it's going to go down by an additional 0.22 standard deviations. So I started, when my calculator is on the desk, I'm at negative 0.07. That's almost flat. In fact, it's not significant, so it is flat. Then what happens once my phone is on the desk and it's on silent? Boom. Why? Because now my positive impulsivity is having a negative effect on my working memory because I am being impulsive about potentially checking what's on my phone. Let's look at that visually. We're gonna run a different code for moderation graphs for categorical, because we're splitting it by categorical levels instead of one standard deviation. Of our moderator is not high, one standard deviation low, it's groups. Calculator, phone off, phone silent. So we're going to use our usual ggplot that we use to graph stuff. X is positive impulsivity, Y is K, working memory, and group is whatever your moderator is. So it says group equals group. That's because in our data, it happens to be called group. Do you see that? That's very important. Make a note of that. Make a note of that. Make a note of that. Otherwise, this will be group. Color is also going to be whatever that's called. And here's what that looks like. And here you can see what this is kind of cool because you can see the simple slope effect almost visually. So if that gray area encompasses a flat line, what does that mean? It's not going to be significant. So you see it already. You see the calculator line? We already knew that that red line was flat. For people in the calculator group, this was not significant. You can see it here too. This red encompasses it. Now, we're never going to trust visualizing. So we can also run our simple slopes, which is the same. You see this? It's the same function that we ran before. Sim slopes, model, predictor, moderator, and you get the same thing. So interesting. What do you notice? Cool result. We already saw this in the betas and the Bs. What happens when I have a calculator on the desk or when I have an off phone on the desk? Not nothing, something happens. What happens? You should have when you're saying what happens, I should hear two variables in there.
There's no relationship between negative impulsivity or.
Good. If I have a calculator on my desk or my phone is off on my desk, my positive impulsivity has no impact on my working memory. What happens when my phone is on the desk and it's silent? As positive impulsivity goes up, so the more impulsive somebody is, what happens to working memory? It goes down. So if you're positive impulsive, maybe put your phone away. Guess what? Spoiler alert, same thing happens with negative impulsivity. By the way, I don't have it in here. Look at the continuous demo here real quick. Remember how we standardized the model? You see that? You can do that in categorical too if you want betas instead. You standardize the model. So this is model PI, standardize model PI, and then run it. You'll get the exact same thing. You'll get betas instead of Bs. It won't work on mine, it'll work on yours because something's wrong with my hour now.